In this section, we are going to prove some important properties of the determinant. Now, up to this point, we've learned how to take the determinant. We've kind of learned some geometric interpretations of the determinant. We've learned how the determinant is affected by elementary row operations. But in this section, we kind of put all the ideas together and really understand why we care what this determinant is telling us. Okay? Now, we're going to start with a lemma. This lemma on its own, not especially important, but it's going to lay the foundation for the important results later in this section. So let A be a square matrix, any square matrix, and let E be an elementary matrix. Remember, an elementary matrix is a matrix where we've just applied one elementary row operation to the identity matrix. That gives us our elementary matrix. Okay? Then the determinant of the product of the elementary matrix times matrix A is equal to the product of the determinants of the two matrices on their own. Okay? All right, so let's get into it. Let's look at the proof. The proof is pretty straightforward. You just make sure you find what the determinant is on one side, you find what the determinant is on the other side, and you just make sure they are equal. You do have to look at every elementary row operation one at a time. Okay? So, case one, suppose E is obtained from I by interchanging two rows. Okay? Then since the determinant of the identity matrix is equal to 1, remember if we interchange two rows, that just swaps the sign on the determinant. So that means the determinant of E would be -1. Okay? So the determinant of EA, remember if we multiply a matrix by an elementary matrix, it just applies the elementary row operation we use to obtain that elementary matrix. So if we obtain elementary matrix E by swapping two rows, then E times A is the same as swapping two of the rows of matrix A. Okay? And we know if we apply that elementary row operation to a matrix and then take the determinant, it's just the negative of the matrix we started with. Okay? Which means that that's going to be equal to exactly this, because determinant of V is -1. So -1 times determinant of A is equal to the determinant of V times A, which is just -1 times the determinant of A. Okay? So that's case one. Case two and case three are very similar. Let me just do one more, and I'll leave you to read the last case on your own. But let's do case two together. Let's discuss it together. The argument is the same. So this time we're going to assume E is obtained using a different elementary row operation. So we obtain E from the identity matrix I by multiplying one of the rows of I by a non-zero constant K. All right? So we know that if we apply this particular elementary row operation, the determinant of the new matrix is K times the determinant of the old matrix. In this case, the old matrix is the identity matrix I. So since the determinant of I is 1, and since we obtain E from I by applying this elementary row operation, multiplying one of the rows of I by a non-zero constant K, then determinant of E should be K times the determinant of I. So K times 1 is just K. All right? So with that, we know determinant of E times determinant of A. Since the determinant of V is equal to K, that's going to be K times the determinant of A, right? Similarly, let's look at the product. E times A, whenever we multiply a matrix by an elementary matrix, that just applies the elementary row operation to the matrix. So since we obtained matrix E by multiplying one of the rows of the identity matrix by a non-zero constant K, when we multiply matrix A by matrix E, that's going to, the resultant matrix is just multiplying that row of matrix A by a non-zero constant k. That's how we get that product. So since this is equivalent to an elementary row operation, we can think of how the determinant affects elementary row operations. And so we know that if we're multiplying one of the rows of a matrix by a non-zero constant k, the result would just be the original determinant times the constant k, which means this will also be k times the determinant of A, and they are actually equal. Okay? In case 3, exactly the same argument. I'll leave you to do case 3 on your own. So the determinant of the product of an elementary matrix and another matrix is equal to the determinant of the elementary matrix times the determinant of the original matrix.